last class we were discussing about the calibration procedures using internal standard, and then I had also referred to some of the interferences that are expected in inductively coupled plasma atomic emission spectrometry. What I had told you in the last class was chemical and matrix interferences are significantly lower with plasma sources compared to other atomizers. However, at low analyte concentrations, the background emission due to recombination of argon ions with electrons would become significant, because the concentrations of the analyte atoms are very small. So, for both single channel and double channel instruments, some amount of correction is necessary, and it is made by taking an average of the background readings on either side of the emission peak. Nowadays, instrument software accomplishes this task automatically or at the discretion of the operator. That means, you also have some sort of a freedom to choose where a peak starts and where a peak ends, so that the total number of counts in that peak area in which you have chosen can be used for calibration purposes. So, spectral interferences, if we want to talk about spectral interferences, they are always possible in ICP analysis, because emission spectra of many elements are rich in lines. Every element will have number of emission spectra, and because we are operating around 6000 to 8000 degree Kelvin, most of the elements will emit emission lines. So, apart from the analyte, you are always getting lot of emission lines with respect to concomitant metal ions present in the sample. So, you have to be very careful in choosing an analytical line where the emission lines of other elements do not overlap the emission line what you have chosen for ICP. That is, for the analyte, the emission line should be chosen in such a way that it becomes specific for the analyte. So, therefore, it is preferable to have a knowledge of other matrix element in the sample, and their emission lines also you should know, and then you have to choose an emission line which has no interference from other matrix elements. The software for ICP instruments in general has number of powerful routines for wavelength selection, calibration, spectral analysis, and deconvolution of the overlapping lines to some extent. Not always, deconvolution is not possible. So, additionally, integrated databases of spectral lines of other elements make spotting and correcting for interferences an integral part of the analytical procedures. So, what happens is, the analytical lines, the moment you want to do an analysis in ICP, the ICP operator will ask you what are the other elements present in the sample. So, you should know what other elements are there in the sample, so that their emission lines should be checked with whether they overlap with the analytical emission line what you are trying to determine. So, for this software helps, because many of these emission lines are already put in the software. So, if it shows you, if you choose a particular emission line, it will show you a list of other elements which have got same analytical line emissions to some extent, or completely overlapping. So, if they are completely overlapping, what you should do is, you have to choose some other line. If it overlaps partially, then software can take care of the interference, because finally, the interference, as I have been repeatedly telling you, interference is only some sort of interpretation, because you are only counting the number of hits on the photon hits. So, the number of counts is what you are always looking for. So, what I would like to do is this, that you should know the elements present in the sample to choose a proper line. So, some of the detection limits, we will not go too much into the interference, but the detection limits I have put in this table, and you can see that in general detection limits in ICP AES are either comparable to or better than flame AAS and more comparable to electrothermal AAS. The following table is this table is very illustrative. For example, here I have put the method on the left side, that is ICP emission, flame atomic emission, and then flame atomic fluorescence, and then flame atomic absorption. And here you can see that the detection limits are less than number of 1 ppb, parts per billion. ICP emission, you can determine approximately 9 elements in quantities less than 1 parts per billion, and between 1 and 10 you have about 32 elements, and between 11 and 100 ppb there are about 14 elements, and 101 to 500 ppb there are 6, and there are no elements in the range above 500 ppb. So, similarly, if you take a comparison of the detection limits using flame atomic emission, that is what we had discussed earlier, the numbers you can see that there are only 4 less than 1 ppb, 12 in the range of 1 to 10, 19 in 11 to 100, and there are 4 elements which are detectable in flame emission above 500 ppb. Similarly, flame atomic fluorescence, if you measure, again the number is very small compared to 9 and 4, and 32 and 14, 14 and 16, and 6 and 4, and more than 500 it is only 3 elements. In flame atomic absorption, there is only 1 element or maximum 2 if you count the hydride generation and mercury, etc. And then 1 to 10 is 14, 11 to 100 is 25, and 100 to 500 is 3, and above 500 is 14. So, you can see that ICP emission spectrometry is quite good in this range, 9 to less than 1 ppb to 100 ppb, quite good. So, it becomes a method of choice for the elements you want to determine the elements in parts per billion level. Here I have said the detection limits of ICP. The table is not very, it contains lot of data. So, the detection limits I have put it in this case, because this is for JY24 2 sigma detection limits for aqueous solutions of single elements. So, here I have listed from silver to iodine, and silver to molybdenum, and you can see that the detection limits are to molybdenum is 1.3, and up to zirconium it is about 2.5, that is with the ICP. Now, you can also see that the detection limits for air acetylene, they are all listed here. For example, for aluminum, if you choose 308.2153 wavelength line, the limit of detection in AES is not possible, that is flame, but in AAS it is about 700 ppm. Like that, I have given you a list of these elements which can be determined in different ranges. So, this thing I am putting it on the NPTEL course, so that you can have a quick reference for the elements you want to determine. These are all continuing up to zirconium. From aluminum to zirconium, almost all the metals and some of the non-metals you can continue, you can have the data at your fingertips. So, you can see that molybdenum, rhodium, molybdenum etcetera, they are all up to 20, and that is the highest resonance line. And suppose you go to 390, that is another third resonance line, it is around 1600. Similarly, you can have all these data for comparison, and this is AES, AAS, atomic emission and atomic absorption. You can see that for selenium there is no detection limit is possible. Detection is not possible, but in limit of detection in AAS is about 50. But if you go to 203.98 line, detection limit becomes 10,000 here compared to atomic emission of 50,000. Similarly, you can take a look at most of the atomic absorption detection limit and atomic emission detection limit. This will help you in choosing different detection, different techniques for the chemical analysis of different elements. Now, you can study this table in leisure, but I am continuing to show these detection limits because it will give you a ready reference. Now, this table shows you for nitrous oxide acetylene flame. Again, you can see that aluminum can be determined up to 20 ppb using nitrous oxide acetylene flame. But if you choose, that is at 309, but 396 if you choose, the detection limit increases to 900 ppb, that is in nitrous oxide acetylene flame. That is, I am comparing the detection limits in atomic absorption as well as in atomic emission, whereas it is 900 here, it is 3 here, this number. Similarly, for barium, beryllium etcetera, I have put all the almost all the numbers, and you can take a look at your leisure. Some of the figures you would be interested to know that zirconium can be determined up to 1000 ppb. This is one of the most difficult elements, and not easy to determine zirconium by atomic emission and nitrous, even in nitrous oxide flame. But if you compare the detection limits for graphite furnace, you can see that aluminum it is not possible, but using 308 line, but 309 line you can determine up to 0.01 ppb using graphite furnace, that is electrothermal graphite, and if you choose 396 it is 600. Like that you can go down the list: antimony, arsenic, barium, beryllium, bismuth, cadmium etcetera. And you can see the cadmium, for example, detection limit is 0.0002 ppb, that means almost up to 2.2 femtograms, that is 10 raised to minus 15, it is possible. Same thing goes, same thing is true for chromium, copper etcetera, they are all 0.005 detection limit. You have to remember here that the detection limits are 2 sigma or 3 sigma, that means the standard deviation multiplied by 2 or 3. So, the quantitative determination is possible even at this concentrations. So, similarly, I have put magnesium and then manganese, mercury etcetera. You can see here mercury determination is up to 0.2 ppb and manganese is 0.0005 ppb. So, the detection limits in general are comparable with ICP with respect and in electrothermal atomic absorption. So, the choice is left to you if you want to determine the elements at parts per billion level for most of the elements using the electrothermal atomic absorption or ICP, the choice falls between the two. So, if you want to determine in ppm level, then the choice is between atomic emission, atomic absorption, flame atomic absorption, nitrous oxide atomic absorption or electrothermal as well as the ICP. So, the detection limits of ICP also I have put it here. Again the same thing what I have shown you earlier, because it contains the this comes along with the comparison. We can even take a printout of this and have a ready reference. Most of the industry equipments come with this kind of data loaded in the computer. So, you will not have much difficulty in working out which method is the best one to determine any element in parts per billion level. Here I am showing you a commercial instrument of atomic absorption. This is flame, this is the nebulizer, and this is the place where the flame comes, and then gases etc. are all connected, and here is the computer which will control most of the operations, and then there is computer, mouse etc. Most of the operations can be controlled here, and then this is for inductively coupled plasma, a bench top instrument which can be used in an ordinary laboratory. This is not portable nor it is easy to keep it in a small lab. Most of such instruments are therefore centralized in any institute. Now, this is a graphite furnace AAS. Here you can see the sample carousel, and then graphite tube would be somewhere here in this range, and then the rest of the instrument will remain the same, just like flame photometer. Now, I would like to close our discussion with respect to ICP and flame atomic emission as well as electrothermal atomic absorption with this presentation, and then I would like to proceed to another technique which we had discussed in the beginning, and that is infrared spectroscopy. Now, this infrared spectroscopy is entirely different from what we have discussed, because infrared spectroscopy is used for the determination of organic compounds, but not necessarily quantitative determination, but qualitative. The maximum use of infrared spectrometry is in the use of qualitative identification of the functional groups that are present in a molecule. So, the discussion here would concentrate on what type of functional groups are there, how to integrate the IR frequencies for the characterization of a compound. This is mainly the domain of organic chemists, but for the sake of brevity, we should also be knowing quite a lot about the infrared spectroscopy, mainly because some of the environmental samples and several other situations will arise where you may have to use pass fail test to determine whether a compound is present or not. It may be in the environment, it may be in an effluent, it may be in a given matrix production unit in a pharmaceutical company, or it may be present in some other matrix such as a consumable, cosmetics, and several other places where infrared spectroscopy would be very useful to identify the various types of organic compounds present in a given sample. So, with this introduction, I would like to take you to the discussion on infrared spectrometry. Now, what is the major difference in infrared and other spectrums, other spectroscopic techniques? The main difference, you can compare, forget about element determination, inorganic elements, but among the organic compounds, so far we have discussed the ultraviolet spectroscopy in for the determination of organic compounds. Afterwards, we have not discussed, but spectrophotometry also can be used for the determination of organic substances present in a given matrix. But taking a look at the ultraviolet and spectrophotometry, in contrast to ultraviolet spectroscopy, the infrared spectrum provides a rich array of absorption bands, which can provide a wealth of structural information, that is how the molecule is there, what type of functional groups are there, etc., in a given molecule. So, it provides methods for studying materials in all three types of physical states, that is either it can be gas, it can be a liquid, or it can be a solid. Analytically useful IR spectrum covers the range of 15,000 to 670 centimeters inverse. That is, after the visible spectrophotometry, if you take a remember our discussion on the electromagnetic spectrum starting from cosmic rays to microwaves and radio waves, etc. This infrared range comes after the spectrophotometry. Then we have a near infrared range, and then infrared range, and then far infrared range. So, if you want to specify different ranges in the spectrum of infrared, you can see that near infrared is range is from 15,000 centimeters inverse to 3,000 centimeters inverse, and in terms of micrometers it is 0.67 to 3.33 micrometers, and the conversion we have already discussed from centimeters inverse to 3.33 in the micrometers earlier in our discussion on the spectroscopy. And mid IR range is the one which starts from 4,000 centimeters to 400 centimeters inverse. This is the range for mid IR. Most of the organic determinations infrared cover this range. Commercial instruments available and maximum use correspond to mid IR region, and in terms of micrometers it is from 2.5 to 25 micrometers. Then there is a far infrared region 200 centimeters inverse to 10 centimeters inverse, and this covers this is equivalent to 50 micrometers to 100 micrometers, 1000 micrometers, not 100, and this is used for coordinate complexes, metal and organic complexes, metallo-organic compounds, and most used is the one 4,000 to 670 centimeters inverse. You can even go up to 200 centimeters also sometimes, and this is the one range 2.5 to 15 micrometers. So, the microns or micrometers were extensively used as the unit of wavelength in the past, but nowadays it is the wave numbers that are the accepted units, and everybody understands wave numbers. It is more easy to remember the ranges. A good organic chemist usually remembers about 400 to 500 functional group frequencies automatically, but for others it may be slightly difficult, but still we can take a look at different functional groups and form an idea about what sort of compounds it can be. A simple reciprocal relationship exists between the wavelength and wave number. So, what is that? That is centimeters inverse is equal to 10,000 divided by wavelength in micrometers. So, micrometers can be converted into centimeters and vice versa. The wave number is directly proportional to the absorbed energy, that is K is equal to E by Hc. That is a very standard formula, whereas wavelength is inversely proportional to the absorbed energy, because both these are reciprocally related. So, there is nothing much to worry with respect to. You can choose either wave centimeters or centimeters inverse or the micrometers for depending upon your convenience, and you can use. I personally prefer the micrometer range. I personally prefer not the micrometer, but centimeters inverse I personally prefer for my work. So, the information contained in an infrared spectrum originates from the molecular vibrations. You can imagine a molecule containing different balls connected with springs. That is how a molecule should be imagined. So, the springs will keep on expanding and contracting depending upon the amount of energy that is absorbed by the organic compounds. So, there are you will find number of fundamental modes. The bonds can be vibrating in different fashions. For example, they may be stretching and contracting in the same plane, or they may be moving back and forth like this. And then these are all. Then there could be complex modes of total molecular vibrational overtones. Two vibrations can combine to give you another peak at double the wavelength or half the wavelength. So, such things are also possible. So, IR analysis may simply involve the characterization of a material with respect to the presence or absence of a specific group frequency. If you get an IR peak at a known position which is there, the compound is there, functional group is there. If you do not have the IR peak at a known position which corresponds to a particular functional group, that functional group is absent. That is how we go about using infrared. So, each frequency or absorption peak what you obtain in IR is associated with one or more fundamental modes of vibration by a complex pattern recognition or by a computer search match algorithm also you can use. I have to tell you that most of the commercial instruments also have computer data stored, so that a given compound will automatically show what are the peaks expected and where are the peaks expected. And you can record the spectrum and simply submit it to the computer for just matching or not matching, and the computer can use these search match algorithms when an unknown spectrum is compared to the existing reference data. So, there are a lot of databases which contain information about the spectrums of thousands and thousands of organic compounds. These databases are sometimes incorporated in the commercial instruments. Otherwise, one can look for specific frequencies what you would like to see. So, when an unknown spectrum must be compared to the existing reference data, if it matches, you do not have to worry at all. You can say confidently that the given compound matches with such a known IR spectrum, and therefore, the compound what you are analyzing is that compound if it matches exactly. But the spectral data is also used to measure one or more compounds in a simple or a complex mixture if the functional groups are different. Suppose you have a mixture where they have this similar functional groups, then you will not be able to use the search and match algorithms. So, one has to be slightly careful in determining these IR spectrum where you are able to obtain the different peaks. So, if you take a look at a non-linear molecule, I would like to remind you that a molecule containing n number of atoms will have 3n minus 6 possible degrees of freedom, that is vibrational modes through which infrared radiation may be absorbed. That means, the degrees of freedom in which a molecule can vibrate is 3n minus 6 if there are n number of molecules. So, for example, methane 9 bands and benzene has got 36 peaks. For example, if you write methane like this, how many elements are there? 1, 2, 3, 4, 5. So, 3n minus 6 this works out to 9. So, 9 modes of vibration. Similarly, if you write benzene molecule, the formula for this is C6H6. So, 12 atoms are there. So, 12 3s is 36. So, 36 minus 9 is 30. So, these are the minimum number of peaks expected. This is benzene, this is methane. So, similarly, as the complexity increases, you can see that the more number of atoms means more number of peaks expected for a given system. So, in order that a particular vibration results in an absorption band, the vibration must cause a change in the dipole moment of the molecule. If there is no change in the dipole moment of the molecule, there is no infrared absorption. So, molecules containing certain symmetry groups will display somewhat simplified spectra. For example, the carbon-carbon stretching frequency, that is in ethylene group, that is carbon-carbon double bond present in ethylene, and the carbon hydrogen stretching frequency of methane, they do not result in an absorption band, because all the CH bonds in methane are equivalent. So, they will all be stretching simultaneously and then contracting simultaneously when IR radiation impinges on the molecule, and there is no change in the dipole moment, because the change in dipole moment occurs only when there is the asymmetric stretching, that is, one should be more, one should be less, etc. The molecule must undergo some sort of a structural change in which the dipole moment must change. So, further, if absorption occurs outside the IR region or too close for resolution, or if it is too weak. There are three possibilities. Outside the IR region it may occur, too close to each other it may occur, or the resolution may be too weak in intensity. The observed number of absorption bands will be less than the predicted number. So, you could always say that even though the minimum number is expected for methane is 9 and benzene is 30, the actual number of IR peaks what you would see would be much less if there is a possibility for the absorption bands occurring some other occurring at outside the region, or if it is too weak, etc. So, you may also see additional absorption bands may occur because of the overtones. That is, suppose we have discussed this presence of overtones earlier, because when we were discussing gratings, and you will see that an overtone band may appear at 1/3 and 1/2 wavelengths with greatly reduced intensity. Such combination bands sometimes do fall in the IR region itself, giving you some amount of confusion, where is this peak coming from? Even though it is not expected, suddenly you will see an overtone band which is of lower intensity, you will not be able to assign. So, if the overtone is possible, one has to be careful. Then we may have combination bands, that is sum of two or more different wave numbers. Suppose there are some of the compounds which are which will reduce the IR frequency absorption, like in ultraviolet we have discussed a similar situation where conjugation in dienes and dinones and then aldehydic groups, etc., they do result in the reduced appearance of a wavelength at longer wavelength, appearance of a peak at longer wavelengths. So, such possibility is there. Then there is a possibility for difference bands, that is two or more wave numbers, the difference that also may appear as a consequence of infrared absorption. So, the molecular vibrations what we have been talking about since such a since last few minutes, I would like to say that a molecule, you should always remember that in the infrared region, a molecule must essentially resemble a system of balls of varying masses, that is hydrogen is 1 and then oxygen is 8, carbon is 12, like that different atomic masses of elements combine to give you an organic compound. So, the range in which the wavelength in which the atoms are organized in a given organic compound depends upon the bond length, and the bond length, the strength of the bond also varies depending upon the functional groups. So, there are two kinds of fundamental vibrations in a given molecule. One is stretching frequency, just like what I was trying to tell you, in the same axis. It is just like pulling a rubber band, holding it in your hand and pull it both sides, that is known as stretching frequency. And then you take a spring on which you put a ball and then shake it, and then it will be moving above, that is in the vertical plane. So, there are basically two types of infrared frequencies which you will be able to recognize in infrared spectrum. For example, one is stretching, in which the distance during stretching, what happens? The distance between the two atoms increases or decreases, but the atoms remain in the same bond axis, that is stretching frequency. And then bending frequency is the one in which the position of the atom changes with respect to a predetermined axis, that is bond axis. So, you can see that the bond axis in general, you will see that changes during bending operations. So, the various stretching and bending vibrations occur always at some certain quantized frequencies. This you should never forget, because in most of these spectroscopic techniques are put on a great foundation of quantum mechanics. So, when infrared radiation of the same frequency is incident on the molecule, the energy is absorbed and the amplitude of the vibration increases correspondingly. When the molecule reverts to the ground state, what happens? The absorbed energy is released as heat. There is no other way the absorbed energy can be used up. So, if you take a look at the molecular vibrations, take a look at this slide. I have 3 atoms here, 3 balls. Of course, you have to assume that they could be of the same element or they could be of different elements, and this is known as stretching frequency. These two are known as stretching frequencies, in which the atoms could be stretching at the simultaneously. That is, for example, if you look at my hand operations, for example, if I pull them, both stretching, and both could be stretching simultaneously, but another possibility exists that one could be stretching, another could be contracting. So, 2 possibilities are there during stretching operations. So, when you take a look at this slide again, here both molecules are stretching away from the central molecule, whereas in this case one is stretching away, another is stretching towards. So, these 2 possibilities always exist in infrared spectrum. Now, I have come to bending vibrations. So, they could be in plane deformations. For example, if you take a look at my hand movements, you will see that they could be stretching in the same plane, that is vertical plane. They could be stretching in the same way. So, they could be going towards both of the molecules, or they could be going like this, or one could be going like this, one could be coming out, one could be stretching, another could be contracting. So, again there are 2 possibilities here. One is this is known as rocking, when both elements, both the atoms are moving in the same direction, but they are all in the same plane, and here they are trying to come nearer, one is stretching, another is contracting. So, these 2 possibilities are there, and another possibility is like this, that is, if I show you by hand like this, that what you would be observing, not in plane, but out of plane, that is, both of them could be going back and forth. Earlier I had shown you like this, and stretching is like this, and in plane is like this, they are going in the same plane, and out of plane is they could be coming towards you or towards you as an observer, or they could be going back, or one could be coming towards you and one could be going away from each other. So, this is known as wagging, when both of them are approaching the observer in the same, in different planes, and here it could be one could be coming towards you, one could be going away from you. So, these are the different kinds of bendings vibrations. In general, bending vibrations require less energy than stretching frequencies, because for stretching you need more energy to pull them, but bending energies require very less energy. So, if they require less energy, where the bond should occur? Towards the longer wavelength region. If it energy intensive processes will occur towards the shorter wavelength region. So, the stretching vibrations in general appear, that is stretching frequencies will appear at shorter wavelengths, and then bending vibrations will occur at the longer wavelength in a given infrared spectrum. So, the stretching vibrations are also found to occur in the order of their bond strength. A single bond, you can imagine different types of bonds present in a given molecule, that could be a single bond, double bond, triple bond, etc. So, in general, triple bond means molecules are, the intermolecular distances are very less, that means the atoms are held very strongly, and compared to that a double bond would be held less strongly, and single bond would be held, bond length would be longer. So, they would be held still less strongly. So, if you take a look at carbon-carbon triple bond, here you can see that the wavelength is 2300 to 2000 centimeters inverse. In this range, carbon-carbon triple bond frequency is expected. Compared to that, look at carbon-carbon double bond. Here it appears at 1900 to 1500 centimeters inverse. So, if you have a compound in which a stretching frequency appears in this range 1900 to 1500 range, you can see that it could be you can infer actually that it is a double bond, it is an ethylenic compound, it is not an acetylenic compound. Similarly, if you take stretching frequencies of carbon-carbon single bond, carbon-nitrogen double bond, single bond, and carbon-oxygen single bond, you can see that the range is 1300 to 800 centimeters inverse, still lower, longer wavelengths. And then if you take hydrogen, here I am putting all the hydrogen in as common, and here I am changing nitrogen, carbon and oxygen. These stretching frequencies occur around 3700 to 2630 centimeters inverse. You do not have to remember all these numbers, but with practice it will come, but it will be good to know that stretching frequencies are always more energy intensive. So, suppose I change this hydrogen to deuterium, then what happens? The range is 2630 and OH stretching frequency actually is 3500 centimeters inverse. You can see that it is the heavier atom, and it could be more symmetrically matched and less energy is required. Like that we can infer lot of information. We can get lot of information depending upon the presence of peaks, either due to stretching frequency or due to bending frequency, single bond, double bond, and then same atom, different atom. So, it is always like this, that you keep on getting lot of information. So, where is the bottom line? The bottom line is an approximate value of the stretching frequency. Is it possible for us to calculate or not, to know by theory? The answer is yes, you can calculate where a frequency is expected, provided you use this formula. The frequency is given by 1 over 2 pi c square root of k divided by mx my divided by mx plus my. Here it may look very complicated to you, but actually it is not. Here k represents a force constant, that is the strength of the bonds. Approximately for single bond, double bond and triple bond, it is about 5, 10, 15 into 10 raised to 5 dynes per centimeter. For single bond it is 5, For double bond it is 10, and for triple bond it is 15, and 10 raised to 5 dynes per centimeter is common. And you know the other numbers. This is frequency, and pi is 3.142, and c is the velocity of light, and this mx and my are the atomic masses present in the compound. So, mx, my and mx divided by mx plus my, this quantity is known as reduced mass. You can write like this: mx my divided by mx plus my square root. This is known as reduced mass. This is a consequence of the quantum mechanical calculations, and the information you can simply calculate using the atomic numbers, and then you can see that the reduced masses must be used to approximately guess the or exactly guess the infrared spectrum. But of course, it is not always at the expected place because of several other constraints, like the presence of solvents and interaction, solvent-solvent interaction, solute-solvent interactions, etc. But in general, you can guess where a compound or a given bond should absorb infrared region frequency. Now, let us come to the instrumentation. In most of the modern commercial instruments, infrared instruments fall into three categories. One is grating dispersive, another is filter dispersive, and another is Fourier transform infrared spectrometer. These are different kinds of commercial instruments. Whatever be the type of instrument, what you need essentially are the main optical system is what you need, and then you need a source of infrared energy, and you need a separate sample compartment in which to place your sample, take it out, etc. And you need a detector to gauge the changes in the infrared spectrum energy, and the electronics and data handling nowadays part and parcel of most of the equipments. So, whatever the forms of operation, mode of operation, the spectrometer forms the heart of the instrument. It takes the broadband infrared radiation, and spectrometer cuts into different wavelengths, so that you can tune the different wavelengths and then choose what wavelength range goes through your sample. So, it splits into ultimate discrete frequencies or wavelengths with a given spectral resolution. This may be performed directly with a monochromator. You can do it in a monochromator in a dispersive instrument, or you can do indirectly by Fourier transform instrument. We will see what is Fourier transform instrument after a short while. In Fourier transform, what you use is an interferometer assembly, that is, it is known as modulator. It produces an output in the form of a modulated infrared beam, which is decoded to produce the final infrared spectrum. It is more of a mathematical operation, but nevertheless, it is a great advance in the IR instrumentation. So, among the monochromator instruments, we will come back to Fourier transform once again after some time. Among the monochromator instruments, the monochromators range from simple filter based instruments. You can just use source, filters, and then infrared sample compartment and optics, and you can use double prism grating instruments, double prism grating, grating 2 grating instruments. You can use and then both Littrow and Czerny Turner mountings are useful, although the former is more useful because Littrow is more compact, and which is provided. The earlier instruments were mostly prism based, which provided simple wavelength scan in micrometer, that is linear scale, basically non-linear scale in a prism. And nowadays Littrow designs with one or more diffraction gratings we are using, and the gratings are driven by very small increments using a stepper motor, which is programmed into non-linear fashion to produce a linear output in wave numbers. That means, you move the motor non-linearly to see that with every movement of the motor you get a linear increment in the wavelength. It is possible, very simple, and commercial instruments they all do this very routinely. And the full range of a grating spectrometer may be 4000 to 600 centimeters inverse. You can buy an instrument from 4000 to 600 centimeters inverse, or 500 to 200 5000 to 200 centimeters inverse. Both are useful for infrared spectrum. Gratings are normally operated in second or third order. Usually spectrums in 4000 to 2000 centimeters inverse are operated always on in the second order, whereas 2000 to 400 centimeters inverse wavelength range you should operate in the first order. A series of cutoff and bandpass filters are placed between the monochromator and the detector to ensure that the correct order of the wavelengths is maintained. That means, if you have from 5000 to 200 centimeters inverse, you should automatically change from second order grating to first order grating output. So, this is achieved automatically by synchronizing with the scanning of the grating. The grating will be moving slowly in the second order. The moment it comes to a particular wavelength, it will change to first order, so that you can have a good control over the wavelength accuracy. In more expensive instruments, only first order grating is used, because that is the most accurate for all the gratings to provide optimum performance, which is maximum overall the output range, because in the first order only you will get the maximum output range. So, a grating blazed at two angles performs as two gratings. You do not have to have two different gratings, but you can blaze them at two different angles, and the drive is reproducible by 0.01 centimeters inverse. So, we will continue our discussion on this after in the next class. So, thank you very much.